We're now continuing our stellar evolution lesson. We already did the low mass stars and saw how they went from a nebula to a black dwarf. Now we're getting into the high mass stars. High mass, obviously a lot more massive than our sun. The start of the evolution of high mass star is just like the low mass star. So I didn't go into it slide by slide because you already saw it. So it's going to start as a nebula, this cloud of hot gas and dust that starts to swirl. It swirls into a nebula. Nebula continues to contract in heat and it becomes a main sequence star. Now it's probably going to be a blue star. It's going to run out of its hydrogen, contract, expand to a giant, fuse helium to carbon. Now at this point is when things start to change. We need to do this end part. So we said this in the giant stage is fusing helium to carbon just like we had before. Now you see it's probably going to be a blue giant. It's hotter, a little bit more massive. After the giant contracts and heats, it's going to expand as supergiant. Okay, so that giant is going to run out of helium. It's going to contract. When it contracts, it gets really, really hot, and there's a ton of pressure because it's so high mass. The gravity is so great that the temperature and pressure in the core is high enough to fuse hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to silicon, and silicon to iron. So we see in this picture here, we have iron forming in the center, silicon around it, oxygen, carbon, helium, and hydrogen. So a lot more layers than we saw with the low mass. Here's a picture of Betelgeuse, which is right there in the constellation Orion. So it's fusing all these things, using its fuel quickly. Eventually, it's going to run out of the fuel it's fusing. When it does, the outside of the supergiant is going to remain the same size, but the intense gravity causes the core to collapse. The center collapses. The pressure increases, and within a fraction of a second, the core is going to explode, and the shock wave blows the star apart. That's called the supernova. So the supernova is that huge explosion of the star. The supernova is incredibly bright, over 100 times brighter than a nova. Only in a supernova does the pressure and temperature get great enough to fuse iron into the heavier metals. So that's how we have all these heavier elements are from supernovas. The pressure and temperature get so incredibly great in the explosion. The core of the supernova then may contract into a very small but dense ball of neutrons called a neutron star. You see one in this picture. One spoonful of a neutron star would weigh 100 million tons. A neutron with a star with a mass of the sun would have a diameter of only 30 kilometers. Some of the neutron stars spin, or most all of them spin, but some of them have really intense magnetic fields, and it causes the radiation to only be emitted in beams out parts of it. And our group, our astronomy group, that's going to talk about pulsars, will talk about these special types of neutron stars. Okay, so supergiant explodes into supernova. The center can collapse into this really dense ball of neutrons called neutron star, or if it's too massive, it contracts even harder and contracts into a black hole. Gravity is so great that even light cannot escape. This is not a real picture, okay, just a artist's interpretation of what it is, showing the black hole, not even light escapes, and the gravity is disrupting all the light from all the other stars around. Again, we're not going to talk much about black holes because another one of the astronomy groups is going to talk about black holes and tell us all about it, and going into one, and all that kind of good stuff. So we look back at our chart here, and we kind of see, again, just a little recap of what we've had. It starts off as a nebula. So the high mass starts off as a nebula. Nebula is a cloud of gas and dust. It starts to condense, and it starts to spin. As it condenses and spins, it turns into a protostar. The protostar continues to contract and heat. It gets to 10 million degrees. hydrogen starts fusing into helium, and it becomes a giant. We don't have the giant. Where is our giant? So giant, like in here. You're going to run out of hydrogen. It's going to collapse, get hotter, fuse helium to carbon. Okay, forms a supergiant. That will run out, collapse again, then it'll get hot enough and dense enough that it fuses all those other elements that we talked about. Eventually they run out, it collapses again, and it explodes in a huge supernova. The center of that supernova may then collapse into a neutron star or a black hole. Okay, so you see the high mass, we kind of jumped around a little bit here to try to get all those parts in. The lifetime of a star may last over 200 billion years or as short as 5 billion years. The length depends on the star's mass. Which stars live for a long time? The low mass ones or the high mass ones? The low mass. The low mass live for a long time because they use their fuel slowly. The large mass ones use their fuel quickly and die quickly. Okay? So one of these might only be 5 billion years long. It uses all of its fuel and then blows itself apart. Whereas it takes many, many years for this to happen. That's why we have black holes, but we don't have black dwarfs. The universe isn't old enough to have black dwarfs, but it's plenty old enough to have lots of black holes. And that's it for stellar evolution. This picture just, we can kind of talk about, okay, what are the different parts? We have our nebula going to our protostar, to a star, to a red giant, and really don't have the white dwarf, black dwarf in here. So just a little picture to kind of sum up what happens again. That's it for stellar evolution.